Hello dear students, I welcome you to Biology Decrypted, and this series on biochemistry, that is Biochemistry Decrypted, is going on, and thank you so much for your support with this series. Now let's talk about this particular lecture. This lecture that I'll be conducting today is lecture number 4 of the series, and we'll be talking about Chemistry Fundamentals Part 4. Now, coming to Chemistry Fundamentals Part 4, we will be talking about water, we'll be talking about pH, and also about the concept of buffers and their action. So this particular lecture is based on water, pH, and buffers. Now, let's start talking from a chemistry point of view. Let's talk about the structure of water. And water, as you know, is the elixir of life, and life is possible because of this thing called water. So let's talk about it, and this lecture is kind of a tribute to this beautiful compound called water. Water, or H2O, has a hybridization. If I talk from bonding point of view, it has a hybridization of sp3. So it has a sp3 hybridization. And what would you predict from this? You would obviously predict that it must look just like methane. So talking about methane, this is how methane looks like, CH4. So methane is CH4, and this is how methane looks like. So this one is, this, as you can see, is out of the plane, and this is into the plane, going into the plane, and these two are on the plane itself. Now, what would you expect? See, so let me tell you again, this is known as a wedge, and this is known as a dash. A wedge projects out of the plane, and a dash projects into the plane. Now, this molecule of methane has a tetrahedral geometry. So this has a tetrahedral geometry. And as you can see here, this is how a tetrahedron looks like. Tetrahedron has 4 triangular faces. As you can see here, this is one triangular face, this is another one, this is another one, and this is the 4th one. So there are 4 triangular faces in a tetrahedron, and this is how tetrahedral geometry looks like. Now, in case of tetrahedral geometry, there is something very important to note. The bond angle here, like all the angles here, will be equal to 109 degree 28 minutes, or let's say it is 109.5 degree. It is 109.5 degree, that is the bond angle, and the carbon has a hybridization of sp3. In a similar way, in a very similar way, oxygen also has a hybridization of sp3. And if we talk about the structure of water, let's draw it. So how we can represent it? Here we have oxygen in the center, then we have 2 hydrogens in this way, and now there are 2 lone pairs, one is projecting in this way and the other is projecting in this way. Somewhat it looks like a tetrahedron, but there is a difference. Obviously, oxygen has a hybridization of sp3 here, but the structure is not determined based on these lone pairs. What actually determines the structure, or what actually forms a part of the structure or geometry, is the bond pairs and not the lone pairs. So we don't consider the lone pairs here. This is the actual structure. In this case, it was a tetrahedron like this, but here it is not a tetrahedron because we don't consider lone pairs to be a part of the geometry. What we see here is the geometry can be called as angular, or we can say it is a bent structure. So we can call it as angular or bent structure. And also there is polarity between, the bonds are polar. You can see there is an electronegativity difference between hydrogen and oxygen, and because of this, this hydrogen has a partial positive charge, this hydrogen has a partial positive charge, and these lone pairs, oxygen with lone pair has partial negative charges. Now, let's talk about the structure of water again. Let's draw this bent kind of a structure. So what we see here is, this is how HOH can be written for H2O. And what we see here is the bonds are polarized, partial positive, partial negative, partial positive. And now if we try to actually sum up, also we'll draw the lone pairs. Now if we try to see each of these bonds, each of the OH bonds, and we try to encircle it, what we see is each of these bonds has individual dipoles. This is a bond dipole. And similarly, this is also a bond dipole. And this is how, if you look at the dipole moment, there will be a dipole moment here, and there will be a net dipole moment in this particular direction. If you actually consider it as vectors, you can actually figure out the direction of net resultant dipole moment. And this shows you the direction of net resultant dipole moment. Now let's move forward. You can see a structure here. Actually, this structure is of water. And what you see here is an envelope. This is how you can see a complete envelope around the structure of H2O. Actually, how we draw H2O is like this. We simply write HOH and we just show the lone pairs. This is how we represent it. But actually, if you look at the molecules look like this. This is how the actual molecules look like. Even if you look at lipid structures and all, this is how you draw the this is how you draw the ball diagram of such molecules, and this is how they roughly look like. This is not the actual picture of the molecules. Molecules actually look round and round like this. So this is how the molecules actually look like. So this takes into concern the van der Waals envelope. So let's write it. This is van der Waals envelope. Now let's consider this important concept. See, there will be lone pairs here. Obviously, oxygen would have its lone pairs. Now, what you see here is very important. You can see here that oxygen has a van der Waals radius. So this is oxygen, and oxygen will have a net radius. And if you try to draw a circle, this will be the circle. This will be the circle of which oxygen is a part. Then hydrogen also has a van der Waals radius. See, if you try to draw it like this, this is how it will be for this hydrogen, and similarly for this hydrogen. And there is this oxygen here. So this is how these individual atoms will have a van der Waals radius, and there will be a value of this van der Waals radius. Van der Waals radius for oxygen will be 1.4 angstroms, and similarly van der Waals radius for hydrogen will be 1.2 angstroms. Now this is how you can see the van der Waals envelope here. And now if we talk about the individual bonds, there are two similar types of bonds, that is OH bonds. And in these OH bonds, if you can see, OH covalent bond distance is 0.958 angstroms. So this gives you the overall picture of the structure of water. And there is something important to note. Did you notice here, despite having sp3 hybridization, the bond angle here is not 109.5 degrees. Rather, it is 104.5 degrees. Why such a difference? Why there is a difference of 5 degrees here? Well, there is a reason. There is a reason hidden in chemical bonding. Let's talk about it. Actually, the concept involved here lies in VSEPR theory. Now, what is VSEPR theory? I hope you must have read about it in chemical bonding in your class 11th. So, VSEPR theory is valence shell electron pair repulsion theory. So this is the basic theory called VSEPR theory. And if we talk about VSEPR theory, there is an order. So if we talk about valence shell electron pairs, either these electron pairs can be lone pairs or they can be bond pairs. This is how electrons are involved in bond pairs. So there are different types of combinations of interactions. There are combinations of repulsions. If we talk about the magnitude of repulsion, if we talk about the extent of repulsion, it is maximum when lone pairs and lone pairs interact, as compared to lone pair bond pair, and finally bond pair bond pair. So the order is, the magnitude of repulsion is maximum in case of lone pair interactions, then for lone pair bond pair interactions, and it is the least for bond pair interactions. And this is the order of repulsion. This gives you a decreasing order of repulsion between valence shell electron pairs. Now, if we talk about lone pair repulsions here, obviously there is a lone pair here, there is a lone pair here, these will be repelling each other. This is how they'll get repelled. And if you see, here is a bond pair, here is a bond pair, and bond pair lone pair repulsion is also taking place. Also bond pair repulsion is taking place, but since there are two dominating interactions, that is lone pair and lone pair bond pair, so what will happen is this bond angle would shrink from an ideal value of 109.5 degree to a real value of 104.5 degree, and it would obviously assume a bent structure. So the bond angle here is not the expected 109.5 degree. So it is not 109.5 degree. What it actually is 104.5 degree. And this is something very important to note. I hope you have clearly understood this particular concept. Now, let's move forward. Let's talk about the concept of dipole moment. If we consider the structure of water again, this is how you can draw this. HOH. This has a partial positive charge. This has a partial negative charge. Obviously, this bond itself behaves as a dipole, and you can see this is actually behaving as a dipole because there is a huge electronegativity difference between O and H. There is a huge electronegativity difference. Obviously, oxygen has a higher electronegativity as compared to hydrogen, and therefore it is keeping the electrons towards itself. Therefore, it has a partial negative charge. Similarly, this hydrogen also has a partial positive charge. And if you see here, this is how the bond dipoles, the individual bond dipoles will look like. This is how the individual bond dipoles look like. And if you try to extrapolate this, if you try to draw this in this way, similarly this one in this way, you are bringing them closer to a single point. And now if you're trying to take the resultant of this, you will actually find that this gives you the net resultant dipole moment. And dipole moment, since it is represented by the symbol mu, so this is your net dipole moment in this particular direction. Now, talking about this particular bond and also this one, because both the bonds are essentially the same. So this bond has 33% ionic character. This particular bond, OH bond, has 33% ionic character. And if we talk about the data, water has a net dipole moment. Water has a net dipole moment, which we can represent as mu net. This is equal to 1.85 dBi. DBi is the unit for dipole moment. I hope you remember. Now, based on this, we can say that water is highly polar. Water is, of course, highly polar, and this is how you can comment on the concept of like dissolves like. We know that like dissolves like, and this is why polar as well as ionic compounds, polar compounds as well as ionic compounds, they do readily dissolve in water. So they will obviously readily dissolve in water. This is the concept. Now let's talk about the dielectric constant of water. We had already discussed about this, but I will be repeating it again. Water, apart from having a high net dipole moment, water also has a high dielectric constant. So the value of dielectric constant, or epsilon, for water is equal to 78.5. Some books also refer to this as 80, but yes, the actual value is 78.5, but this is very high. This is very high as compared to other solvents, and there are a very few solvents which have dipole moment higher than water. And if you talk about water, well, for all natural processes and for life in general, there cannot be any other solvent which is better than water in terms of polar solvents. Water has the highest dielectric constant for all naturally available solvents. So obviously nature had no other option other than choosing water as the universal solvent and water as the medium for all biological processes, for all life processes. And this is how water is rightly called as the elixir of life. Now, let's talk about water's role as a universal solvent. Now, talking about water as the universal solvent. So, let's put the heading as water, the universal solvent. Now, water has certain specific properties. Water, if we compare water with other liquid, if we compare it with other liquids, so what we will find is water has a sufficiently higher melting point as compared to other liquids which exist as liquids at room temperature. So water has a melting point of 0 degrees Celsius. I hope you know, because this is the temperature at which ice melts and forms liquid water. So this can be written as 273 Kelvin. Now, talking about the boiling point, obviously water has a high boiling point as well. So the boiling point of water is also high, and it is 100 degrees Celsius, and obviously in Kelvin it will be 373 Kelvin. Apart from this, water also has a high heat of vaporization, and also it has a high value of surface tension. And surface tension is a very common property of water because it tries to minimize the surface. Now, I hope you might have noticed this while taking a bath. Whenever shampoo or soap solution falls on the on the tiles or floor of your bathroom, what you observe is the thin film of water which is there, it suddenly goes away. Whenever there is this soap solution falling, this whole film, this recedes away. Why does this happen? Because the surface tension of water is disturbed because of these surfactants or detergents. So water generally has a tendency to somehow reduce the surface area, and therefore we call it we refer to it as tension. So it is always in a tension to reduce the surface area. This is the general tendency of water as thin films. Now, talking about water, for water to have all these properties, doesn't it seem abnormal or anomalous? Because water, it hardly has a huge molar mass. Like, we cannot even compare the molar mass because it is too less to compare. The molar mass for water is 18 grams per mole, which means 1 mole of water, that is 6.022 into 10 to the power 23 molecules of water, weigh just 18 grams. So this is actually very less. And to have these properties with this particular molecular weight is even more shocking. So what actually is the reason behind so many unique properties? Well, the answer lies in bonding. The bonding which is shown by water is extensive amount of hydrogen bonding. And this hydrogen bonding is responsible for almost all of the properties shown here. So H2O or water, there are many water molecules surrounding, and these will have hydrogen bonds. There will be hydrogen bonds being formed, and the main reason behind bearing such amazing properties is hydrogen bonding. Now, if we talk about hydrogen bonding, this is also the reason why water is a liquid at room temperature. This is a major reason why water is a liquid at room temperature. Now let's talk about the structure of this hydrogen bond. So what we see here is there is a molecule of water like this, and this is the hydrogen. There are two lone pairs here. This obviously is acting as the donor. This is the hydrogen donor here. Now what happens next is another water molecule comes in this way. This is the oxygen. There is one lone pair here, and there is another lone pair here, and here is hydrogen, and here is another hydrogen. This is acting as hydrogen bond acceptor. And now a hydrogen bond is actually being formed between oxygen and hydrogen. So what we see here is this particular hydrogen bond. This is the hydrogen bond that is formed, and obviously you can see, since this is between two molecules, two different molecules, we'll call it as intermolecular hydrogen bond. Now let's talk more about this concept of hydrogen bonding in water, because hydrogen bonding is not only seen in liquid water, it is also seen in ice, and this is the reason why ice actually floats on water. So let's talk about it. Here we will draw a water molecule like this. Now this water molecule will obviously be surrounded by other water molecules, and we can say that this is how there are water molecules surrounding this particular water molecule. Let's say here you have HOH, you have HOH here, you also have HOH here. Let's talk about these four water molecules. What can happen here is hydrogen bonds can be formed here, 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 as well as here. Now, since this hydrogen is partially positive, partially positive, partially negative, partial negative, partial positive, partial positive, partial negative, partial positive, and this is how we can show it for all. This is how we can show it for all. This is how we have shown it. Now hydrogen bonds can obviously get formed here, 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 as well as here. So what we can see here is one water molecule. Let's say we are just talking about this particular water molecule. This one is forming 4 hydrogen bonds. This is how it is forming 4 hydrogen bonds, and like this many other water molecules. Each water molecule can have a maximum tendency to form 4 hydrogen bonds each. So this is somewhat the structure of ice. Well, the structure of ice is more ordered. Actually, it forms cage-like structures. It is just similar to the tetrahedral arrangement. It is just like this. These kind of ordered cage-like structures are formed. So cage-like structures are formed in case of ice. Whenever we have ice, there are cage-like structures, and What is stored in these cages? Actually, it's air. And this is why ice has a lower density as compared to liquid water. Now, talking about ice. In case of ice, that is solid water, we can also refer to ice as solid water. In this, each water molecule, each H2O molecule forms 4 hydrogen bonds. Obviously, the hydrogen bonds formed here are intermolecular. Now, if we talk about liquid water, what we see, what we observe is for every 10 water molecules, there are approximately 34 hydrogen bonds. So this boils down to 3.4 hydrogen bonds per water molecule. So this brings it down to 3.4 hydrogen bonds per water molecule. This does not mean that the bonds are fractional in nature. This is just a number to represent it on the basis of one water molecule. So this is how we have taken an average for 10 water molecules. There will be approximately 34 hydrogen bonds, and that's how for one molecule there will be 3.4 hydrogen bonds each. So now talking about the density. If we talk about the density, if we compare the density of ice and water, what we can easily comment is the density of ice is lesser than water, the liquid water, and that's why ice floats on surface of water. This is the reason why ice floats on the surface of water, because of having a lesser density, since it has cage-like structures, since it has air trapped in it. Now, coming back to the concept of dielectric constant once more. Let's talk about dielectric constant and solvation. We know about solvation. I told you about solvation in the very first lecture. So, talking about a high dielectric constant, water obviously has a high value of dielectric constant, which is, to be accurate, it's 78.5, and this is much high. And also, some books refer to it as 80 as well. So now, what is the role of dielectric constant? Why does this matter? Why does this high value of dielectric constant matter? Why does it make water a very good solvent? Well, I hope you remember the concept of Coulomb's electrostatic force of attraction. Yes, the formula is F is equal to 1 by 4 pi epsilon Q1 Q2 upon R square. Now here, this is the formula for electrostatic force of attraction. Now, or we can just say electrostatic interactions. So this is the case for electrostatic interactions, and if you talk about electrostatic force of attraction in general, or we can say Coulomb's force. Now, what we see here is this particular term is the dielectric constant. And why does this matter? Actually, the role of dielectric constant, or we can say what actually dielectric constant is, it is actually the capability to neutralize the force of attraction, between charges. And obviously, if we take an example of NaCl, let's say Na plus Cl minus, obviously they will have strong electrostatic forces of attraction. And in order to break these electrostatic forces of attraction, obviously new interactions will be forming, and this property of a high dielectric constant makes it possible, makes this process of solvation possible. And A high dielectric constant is directly proportional to the extent of solvation, and when water is the solvent, it is also called as hydration. And you know about hydration, right? That these kind of hydration spheres are formed by water molecules, because water molecules will be surrounding these particular charges in this way, and this is how many water molecules will be surrounding, and this is how solvation spheres will be formed, and eventually the bonds, the strong electrostatic forces of attraction between these particular charges will break and they will separate, they will be dissociated in water, and they will be finally solvated. So this is the overall concept of solvation or hydration, whatever you call it. Now let's move forward. We have understood sufficiently about the structure of water. Now let's talk about the functional aspects of water. Let's talk more about the chemistry of water. Now, to talk about the chemistry of water, we must understand the basics of chemical equilibrium. So let's talk about the basics of chemical equilibrium first. So we'll talk about the basics of equilibrium. Let's consider this particular reaction where A is getting converted to B, and also B is forming A. So what is happening here is there is an equilibrium. There is this kind of an equilibrium where forward reaction is taking place, at the same time backward reaction is also taking place. Backward reaction, or we can also call it as a reverse reaction. So here we can see reactant, that is A, is getting converted into product B, and similarly product B is also breaking down into reactant A. Both these processes are occurring simultaneously, and what we can see here, there will be a rate of this forward reaction, and also there will be a rate of this backward reaction. So there will be a rate for both. Now let's talk about both the rates one by one. First we'll be talking about the forward reaction, then we'll be talking about the backward or reverse reaction. Now first we'll discuss about this forward rate. The forward rate is directly proportional to the concentration of A. Similarly, the backward reaction rate is directly proportional to the concentration of B. Now this is very obvious because it actually depends on the substrate concentration or the reactant concentration, which is A and B for both the reactions respectively. Now if we try to remove this particular proportionality constant, if we want to remove this symbol of proportionality and we want to actually equate it, we have to bring a proportionality constant here. So the constant that we'll be needing here is Kf, and it's very simple. It is actually the forward rate constant, and similarly for this one it will be Kb, that is the backward rate constant. This is how we have the rate constant for the forward and backward reaction, and we can write it as Rf is equal to Kf into concentration of A, and Rb is equal to Kb into concentration of B. This is how we'll actually denote it, and this is equation 1, this is equation 2. Now what we can say, actually the condition of equilibrium, at equilibrium both these rates become equal. So Rf becomes equal to Rb, and now from equation 1 and 2 what we can say is Kf into concentration of A will be equal to Kb into concentration of B. And here obviously what we can do is we can take like terms to one side. So we'll separate the sides, we'll have the like terms on each sides. What we can see here is we get Kf divided by Kb here, and we get B, concentration of B divided by concentration of A here. Now what we can say here is this is the concentration of product, and this is the concentration of reactant. Similarly, both of these, that is Kf and Kb, both are constants. Now, by combining these two constants, we actually get another constant, and this constant is very, very important from equilibrium point of view. This is the equilibrium constant. So this is simply the equilibrium constant, or we call it as KEQ. Sometimes we also refer to it as capital K, but the basic concept remains the same. So at equilibrium, we have KEQ. But this reaction course can be like, a reaction course has more to it than just equilibrium, because equilibrium is just one single part. Apart from this, the reaction occurs throughout. There is a lot of forward reaction happening, backward reaction happening. Equilibrium is just a simple part, just a small part of this whole course of reaction. What about the whole course of the reaction? Won't there be reactant and product concentration there? Obviously there will be. So for this whole course of equilibrium, at this point, at this point, at this point, at this point, in the whole course of reaction, there will be, respectively, for each point we can define a reaction quotient. We can define a reaction quotient Q, which also denotes product concentration by reactant concentration. So this is the overall concept of reaction quotient, just the same as equilibrium constant. The only difference being, this takes into consideration the equilibrium concentration of the reactants and products, whereas in case of reaction quotient, that can be at any point of the reaction. And what we can see here is at equilibrium, this reaction quotient is only known as the equilibrium constant. So basically, this KEQ or equilibrium constant is a special case of reaction quotient itself. And this is a very important thing to note. Now let's talk more about equilibrium constant. If we talk about a particular reaction, let's take an example. For example, we have 2A. This gives you 2A gives you B plus C. This is one example of reaction. Now, if I ask you to write equilibrium constant for this particular reaction, how would you write? Well, it's very simple to represent. We will write the product concentration here, and we'll write the product of product concentrations. So we'll write concentration of B into concentration of C. Then we'll divide it by the reactant concentration. Remember just one thing. One thing is very important to note, that whenever there will be stoichiometric coefficients, this will go into the power. So how will we write it? We'll write A squared. We'll write A squared, and this is how we can write equilibrium constant for this particular reaction. So this is how we actually write the equilibrium constants, and this is the basic concept you needed to know about chemical equilibrium, because this is the maximum we'll cover for biology point of view. What we are actually more concerned about from biology point of view is not chemical equilibrium. Well, we are not studying mainstream chemistry here. We are talking about applications in biology or applications in biochemistry. So what matters is ionic equilibrium, because there are ions, there is concept of pH, there is water, there is ionization, there are acids, there are buffers, there are so many things. And all of this concerns ionic equilibrium more. So we'll be studying specifically ionic equilibrium more in this particular chapter now on. So this was our discussion so far about chemical equilibrium, but the fundamentals of chemical equilibrium will always stay, and obviously ionic equilibrium is an application of chemical equilibrium, no doubt about that. So from chemical equilibrium, we'll shift to the concept of ionic equilibrium. Now, let's move forward. Let's talk about ionic equilibrium. Let's talk about water. Let's come back to the chemistry of water, and let's look at the chemical properties of water, how water gets ionized. Let's look at the ionization of water. So first of all, what is water? Water is basically, as you know, it is neutral. But there are two very important properties. Water is amphoteric in nature. What does this mean? Amphoteric substance is a substance that actually behaves as an acid. It is capable of behaving as an acid. It is also capable to behave as a base. Now, if we talk about simple Arrhenius concept of acids and bases, what we can say is acid is one which gives H plus ions in solution, and base is one which gives OH minus ions in solution. And this is very simple. Well, here when we talk about solutions, we are obviously talking about aqueous solutions. Now, there is another concept. There is another property of water, that water is amphiprotic. Water is amphiprotic. As you can see, amphi means both, and protic means, obviously it refers to protons. Now, water can act as a proton donor, as well as it can act as a proton acceptor. So yes, water can act as proton donor as well as proton acceptor. Proton donor. When we talk about proton donor, we talk about acids. And whenever we talk about proton acceptor, we talk about bases. Well, this is the Bronsted-Lowry concept of acids and bases. So we have seen the Arrhenius concept. This is according to the Arrhenius concept of acids and bases. And this is the Bronsted and Lowry concept of acids and bases, where H plus donor is known as acid and H plus acceptor is known as base, and water can behave as both. Water can act as a H plus ion donor as well as H plus acceptor, and therefore water is amphiprotic in nature. So water is amphoteric as well as amphiprotic. Now there is another concept of acids and bases, that is Lewis concept, in which we say that the one which donates a lone pair is a base, and the one which accepts a lone pair is an acid. So this is the basic concept of Lewis theory of acids and bases. So we have seen all the three major theories of acids and bases. Now let's directly come to the point. Let's talk about ionization of water. So now we'll be talking about ionization of water. Water, as you can see, H2O, it actually can split into H plus and OH minus ions. And water has a unique property of self-ionization, or you can call this as auto-ionization. So water can undergo self-ionization or auto-ionization, and if you see here, there are two water molecules which are reacting. Here, one water molecule is acting as an acid, other one is acting as a base. And now, you should remember that every acid, this is according to the Bronsted-Lowry concept, every acid has a conjugate base, because every acid will give H plus and the remaining part will be known as a conjugate base. Similarly, every base can accept an H plus ion, and it can have a conjugate acid. So every acid will have a conjugate base and a conjugate acid. Similarly, every conjugate base will have a conjugate acid of the base. So now what we can see here is this particular water molecule can behave as an acid, and it can give away an H plus ion. So what remains is OH minus, and this is the conjugate base of acid, and obviously here your acid is water. Now obviously there will be an equilibrium symbol here. Now what happens here is very important. H2O, this splits to give you H plus. Now this H plus is taken up by this base. So this has a lone pair, and this lone pair is given to H plus, and this is how HOH, this ion is formed. H plus ions does not remain free in the solution. Rather, it is actually captured by a water molecule that acts as a base, and it finally forms this kind of an ion, and this ion is known as hydronium ion. This is hydronium ion, or H3O plus ion, as you might be knowing. So this is how H3O plus ions are formed, and H3O plus ions are called as hydronium ions. Hydronium ions. And as you know that H plus ions do not remain free, but yes, these are H plus ions which are captured by water molecule which acts as a base. So this is how H3O plus is conjugate acid of base. So every base will have a conjugate acid, every acid will have a conjugate base. It's as simple as that. Now, talking about hydronium ions, actually the H plus ions concentration is equivalent to the concentration of H3O plus ions, and this is equal to 10 to the power 7 molar. Similarly, the concentration of OH minus ions is also equal to 10 to the power minus 7 molar, and all this can be measured by ionic conductivity measurements. So that's all. Now let's write an equilibrium constant for this particular equilibrium. For this particular equilibrium, we'll be writing an equilibrium constant. So how can we write the equilibrium constant? KEQ will be equal to H plus ion concentration into OH minus ion concentration. We can write it in this way, or we can simply write it as H3O plus concentration into OH minus concentration, however you like it. But yeah, obviously this is a much better way of representation, this one, because H3O plus is the actual form of the species in which H plus ion exists. It doesn't exist in the solution as H plus ions. So now what we'll see is in the denominator we'll be having H2O squared. We'll have H2O squared. Now it's very important to note that this H2O can be considered as simply H2O concentration. This can be considered simply as H2O, and what we'll do here is we'll be multiplying it to KEQ. Since this value will be constant, the value of KEQ is obviously a constant. When we actually multiply it, we get another constant. This is very important to note. Also, if we talk about the degree of ionization, here alpha represents the degree of ionization. Obviously, for water, although water shows self ionization or auto ionization, the degree of dissociation for water is very less, even lesser than many of the acids out there. So what we can do here is we can multiply KEQ into H2O concentration. KEQ into H2O concentration, and since this H2O concentration is constant, this is constant, and what we can say is this value is very high. This is high and this is constant. This doesn't change because since the actual degree of ionization of water is very less, so if we actually compare it to the concentration of water that is available, so obviously water concentration is actually very high, and this value is found out to be 55.5 moles. How can we calculate it? Well, let me tell you one important thing. If we talk about the density of water, the density of water is 1 gram per cc, or we can say 1 kg per meter cube. So it is 1 kg per meter cube, or we can say 1000 gram per decimeter cube, and 1 decimeter cube is equal to a liter. So it is 1000 grams per liter. 1 liter will weigh 1 kg. This is the simple concept for water. Now if we actually try to calculate the molarity, what we'll see is for 1 liter there will be, so obviously the volume is 1 liter. In a volume of 1 liter, obviously per liter there will be 1000 grams divided by 18 grams per mole. Obviously this is 1000 gram, that is the given amount of water you are having, and also the molecular weight of water, that is 18 grams per mole. So 1000 grams by 18 grams per mole, what you get is the value is 55.5 molar. This is how you can easily calculate the molarity of water. And obviously all this measurement is taken at 25 degrees Celsius at room temperature, obviously. Also, if we talk about the KEQ, if we talk about the equilibrium constant, this can also be calculated. This can also be calculated, and the value that we get here is 1.8 into 10 to the power minus 16 molar. So this is how we actually multiply both. We multiply both, and finally what we get is we get this ionic product of water. So what remains here in the equation, since we are already multiplying this, what actually remains is this. These are the two ions, these are the two major ions, that is H plus ions and OH minus ions, which are multiplied, and this is known as the ionic product of water. So H plus and OH minus ions, these are the concentrations are multiplied, and what you get is the resultant, what you get is the ionic product of water. This is known as the ionic product of water, or we can say KW. This is the ionic product of water, and this is very important to note. Now let's move ahead. Let's talk more about the ionic product of water. So this ionic product of water, or KW, is equal to concentration of H plus ions multiplied by the concentration of OH minus ions. Now if the H plus ion concentration is 10 to the power minus 7 molar, also the concentration of OH minus ions is 10 to the power minus 7 molar, we multiply these two, so we get the final value of KW as 10 to the power minus 14 molar square. This is the value of KW that we are getting. Now if we consider H plus ion concentration and OH minus concentration, obviously this will have an equal value, that is 10 to the power minus 7 molar. Now what we can say is, at this value of 10 to the power minus 7 molar, this represents neutral solutions. Now if we go beyond this, for example, if the concentration of H plus ions is more than 10 to the power minus 7 molar, if it is more than that, then such a solution will be termed as basic. This will be basic in nature. Now if it goes below this, then the value will be less than 10 to the power minus 7 molar of H plus ion concentration, and therefore this will be called as acidic. So yes, if we talk about greater amount of H plus ion concentrations, for example, if there is there are lots of H plus ion concentrations, just let me correct myself. Actually, if there is this huge number of H plus ion concentration, for example, if we are talking about OH minus ion concentrations, well, I would be correcting myself here. So if there will be a huge number of, for example, if there is 10 to the power minus 7 molar H plus ion concentration, it will be neutral. If the concentration of OH minus ions, is more than 10 to the power minus 7 molar, if it is more than that, then in this case this will be called as basic, and if it is less than that, then it will be called as acidic. So actually the thing will be inverse. For example, if H plus ion concentration is more, like if H plus ion concentration is more, then it will be called as acidic, and if H plus ion concentration is less, then it will be called as basic. This is the overall concept. So I just corrected myself because I somehow told you something wrong. So yes, just pardon me for this. So this is the overall concept here. Now let's talk about an important thing called negative logarithm. Whenever we take negative log of KW, what we get is PKW. This is as simple as that. Whenever we take a negative log of KW, we get PKW. Similarly, this can be written as negative log of 10 to the power minus 14, and what we get here is 14. So obviously 14 forms the upper limit for the scale. Now let's talk about pH. Whenever we talk about pH actually is the negative log of H plus ion concentration, and if we actually consider this negative log of H plus ion concentration, that is 10 to the power minus 7 molar. So this will be log base 10, 10 to the power minus 7 molar. So what we'll get here is a value of 7. So this is the value of 7 and this represents neutral pH. Now, what we'll see here is whenever pH is greater than 7, it represents basic solution. If it is greater than 7, if pH is less than 7, it represents acidic, and if pH is equal to 7, then it represents neutral solution. So it's very simple. If pH is greater than 7, then it is basic. If it is less than 7, it's acidic, and if it is equal to 7, then it is neutral. Now, based on this, we can actually create a scale for pH, and this is how. So pH actually stands for potens of H. That is a German word for power. So here the scale is from 0 to 14. Obviously, the range is from 0 to 14. There is a pH of 7 in the middle. This represents the neutral pH. This represents neutral pH. Here, this is extreme acidic. This is extreme basic. And here we can see the H plus ion concentration. H plus ion concentration is increasing, and here we can see that now there is one important thing here. H plus ion concentration is decreasing here. H plus ion concentration is decreasing here as we are moving from here to here. What we see here is there are many H plus ions in case of acidic. Acidic will have more amount of H plus ion concentration, and it is gradually going down, going down, going down. And here, as we see, the OH minus ions concentration is increasing as we go from here to here. Overall, what is happening? The pH is increasing. pH is increasing as we move from 0 to 14. So this is the overall concept of the pH scale. Now let's move forward. If we have H plus ions given, for example, if we have H plus ion concentration given, and we are asked what is the pH, how will we find it? It's very simple. pH is equal to negative log of H plus ion concentration. Similarly, if the question gives you the pH, for example, pH is given, and you're asked what is the concentration of H plus ions, what will you do? You'll actually find the concentration of H plus ions as 10 to the power minus pH, or simply what we can call this as is antilog of, we'll take the antilog of pH. We'll simply take the antilog of pH, or we can write 10 to the power minus pH. This is how we can actually represent it, and we can solve questions based on pH. Now let's talk about important concept of acid dissociation. Let's talk about acid dissociation in detail. So for acid dissociation, let's take an example of an acid like HCl. HCl is an acid, and here water, because of its amphoteric nature, it will be behaving as a base, and what we see is HCl gets dissociated and it forms Cl minus. And since HCl is a strong acid, let me tell you about strong acids and weak acids first. Strong acids such as HCl, H2SO4, they have alpha is equal to 1, that is approximately equal to 1, or you can say that the degree of dissociation is approximately 100%. That is, most of it, almost all of it is ionized, but yet we don't say truly 100%, not exactly 100%. We just say approximately 100%. So this is how we should represent the arrow, with a very small backward reaction component. So if we talk about weak acids, now weak acids examples are CS3COOH, H2CO3, etc. Now if we talk about the dissociation of a weak acid, what we see here, Cl minus here is the conjugate base, and obviously H3O plus is the conjugate acid. Now we know the concept of conjugate base and conjugate acid. So this is the conjugate base for this acid, and this is the conjugate acid for this base. Now let us consider a weak acid. So let's take an example of a general weak acid, that is HA, and HA is undergoing dissociation. Obviously in the presence of water it is undergoing dissociation, H plus plus A minus. This is how it is forming the conjugate base and conjugate acid respectively. Now if we write the equilibrium constant, KEQ will be equal to H plus ion concentration into A minus concentration divided by HA into H2O concentration. Now what we can say here is since the degree of dissociation is very less as compared to the concentration of water, what we can do here is we can assume the concentration of water to be constant, and since it is multiplied with KEQ, what we can write here is KEQ into concentration of water, and what we get is HA, product of HA, A minus, and this will be divided by concentration of HA. Now this actually gives you a new constant, and this new constant is Ka, or we can call it as acid dissociation constant. This is your acid dissociation constant, and it is very important to note that Ka is directly proportional to acidity. It is directly proportional to acidity, and Ka can be finally represented as H plus ion concentration into A minus ion concentration divided by HA. So this is your Ka, and Ka is directly proportional to acidity, so if Ka increases, acidity will increase, and vice versa. Now if we talk about an important concept, just like negative log of H plus ion concentration gave you pH, similarly negative log of, let's say I am SSB, so negative log of SSB is equal to PSSB. In a similar way, the negative log of Ka will give you pKa. This will give you pKa. This is something very important, and you should remember that pKa is equal to negative log of Ka, and therefore it will be inversely proportional to Ka as well. If you actually increase the value of Ka, or let's say pKa, by a very similar relation, it will be inversely proportional to acidity as well. If the acidity increases, pKa will decrease. If acidity increases, Ka will increase, and if Ka increases, pKa will decrease. So pK is inversely proportional to Ka. Remember this inverse relationship always. Now moving forward, let's take examples of different acids. For example, if there is an acid, let's say there is a monoprotic acid. For example, there is just one proton that is actually lost when you are adding OH minus ions. Whenever you are adding OH minus ions, what is happening is H plus ions are dissociating, and this is how it is actually OH minus ions are neutralizing H plus ions, and finally it is forming water. So this process is called deprotonation, and based on the number of protons that can be lost, different types of acids are there, just like monoprotic acids, diprotic acids, polyprotic acids, etc. So if we talk about monoprotic acids, the best example is of CH3COOH, that is your acetic acid. CH3COOH is your acid. It will undergo dissociation, and it will have a particular Ka. For every equilibrium there will be a Ka, and for every Ka there will be a pKa. So this will be pKa1, and it will form CH3COO minus, that is the conjugate base, and H plus ion as well. This is the conjugate acid. Now for polyprotic acids, if we talk about polyprotic acids, we can take the example of H2CO3. H2CO3, that is carbonic acid. What happens is it undergoes first dissociation to form HCO3 minus, it is bicarbonate ion and H plus ions. Now this bicarbonate ion, this will undergo further dissociation to form to form H plus and CO3 2 minus ions. So this is how H plus and CO3 2 minus is formed. Now if we look at the titration curve, what is titration? I hope you have done titration in your lower classes or maybe in your college. So talking about titration curves, what do you do here? Actually, you are adding equivalents of OH minus ions. There is a burette, there is a pipette, and there is a conical flask where you are actually adding drop by drop of, say, acid or base, and you are trying to do neutralization. So this is what is actually happening. Here we are actually making this curve. We are plotting this curve. There is pH on the y-axis and there is OH minus ion equivalents in the on the x-axis. Now here you will be measuring the extent of titration. So you can say that here the titration is 0% complete, here it is 50% complete, and here it is approximately 100% complete. Now if we try to plot the curve, here in the very beginning, in this initial phase, what you had is CS3COOH. You simply had your acid. Now gradually it is dissociating, and finally actually you're having increased concentration of CH3COO minus. And similarly, by the end of this, there will be only CH3COO minus when this titration is 100% complete. So what is this? This is basically your A minus ion, that is your conjugate base. Here you have your HA, and here in this midpoint, what will happen is pH is equal to pKa. pH is equal to pKa, and what you actually observe here is both the species are equal in concentration. So the acid and the conjugate base, that is CH3COO minus, both these are equal in concentration, and this zone, this whole region is actually responsible for buffering. This is responsible for buffering action. This is responsible for buffering action. And obviously, what is the role of buffer? Basically, it resists pH changes. So pH changes are resisted by buffers. Now, if we talk about polyprotic acids, again, if we try to plot pH versus OH minus equivalents that are added, what you see here is first there will be one curve like this, then there will be another curve like this. So basically there will be one pK, there will be this pK1, there will be pK2. And this is the case in case of many amino acids as well, where there are multiple groups that can be deprotonated. So this is the overall concept. Now let's talk about the relation between pH and pKa. Very, very, very important relation between pH and pKa. Here we will be talking about the famous Anderson-Hasselbalch equation. So let's take an example of HA. HA is getting dissociated into H plus and A minus. You know that A minus is the conjugate base. This is the conjugate base. Let me tell you one important thing. Generally, this conjugate base is also surrounded by a counter ion. Like if there is an anion, obviously this conjugate base is an anion. So there will be a counter ion, that is a cation, along with it. Now, if we take an example of CH3COO minus, CH3COO minus is the conjugate base. There will be a cation like Na plus here, and therefore this will exist as a salt. This will exist as a salt, and salt here is nothing but, whenever we are talking about the salt, we are obviously talking about the conjugate base, because Na plus will get solvated. What will actually be there is your CH3COO minus. That is your salt. Now that is your conjugate base, let's say. Now if we write the Ka here, Ka will be equal to H plus ion concentration into A minus divided by HA. Let's say this is the salt concentration and this is the acid concentration. Similarly, these expressions can be written for bases as well. There we will be writing Kb and we will be taking example of bases. Now, let's just circle these two together. Let's keep it together like this. This ratio should remain as it is, and this part of H plus ion concentration will remain separate. Now, let's do an important thing. Let's take negative log. Let's take negative logarithm on both sides. We'll take negative log on both sides, and what will we get here? We'll get negative log of Ka, and this we will take negative log of this whole term, that is negative log of H plus into A minus by HA. Now, there is something important to know. If we talk about the log rules, log mn is equal to log m plus log n. Similarly, if there is negative log of mn, we will have negative log of m and negative log of n. Very simple. This is how we actually denote it. So this is how we'll do it. So negative log of K will be negative log of H plus ion minus log A minus upon HA. Now, we have come to an important point. Let's identify this. This is negative log of Ka and we can call it as pKa. This is negative log of H plus ion concentration and we can simply call it as pH. And what we see here, this is the salt concentration, this is the acid concentration. So what we can write here is pKa is equal to pH minus log salt upon acid. What we can see here is pK is equal to pH minus log salt upon acid. Now, if we try to rearrange, what we can write here is pH is equal to pKa plus log of salt, concentration of salt upon concentration of acid. So this is a very important equation, and this equation is known as the Henderson-Hasselbalch equation. This is the famous Henderson-Hasselbalch equation. And what we can do here is we can write an expression for this. That is, let's say, let's take an example. What if the salt concentration is equal to the acid concentration? Well, in that case, the ratio of salt and acid will be 1. Obviously, this ratio of salt to acid, this whole ratio will be 1. And when we have log 1, obviously base 10, there is base 10, the value of log 1 will be 0. And if log 1 is 0, in that case, this whole thing will become 0 and pH will be equal to pKa. Also, the converse is true. The converse is true. So what we can say is when pH is equal to pKa, then obviously the concentration of A minus, that is the concentration of salt, will be equal to the concentration of acid, and this is the point where the acid will be 50% dissociated. This will be the point where the acid is 50% dissociated, and this is also an important point to note. Now, let's finally come to the concept of buffers. Let's talk about buffers. Now, if we talk about buffers, what are buffers? Buffers are responsible for resisting, so they resist change in pH. For example, if you are adding an acid or a base, what happens is it actually resists the change in pH, and here the concept of common ion effect works. There can be different types of buffers. There can be either acidic buffers, there can be basic buffers. So yes, acidic buffers, basic buffers, etc. For example, if we take examples of acidic buffers, the physiological buffers, we have bicarbonate buffer. We also have phosphate buffer. These are example of physiological buffers that we find in living systems. Now, talking about acidic buffers, what is actually what is the constituent? If you talk about acidic buffers, it is made up of weak acid and the conjugate base. Weak acid and its conjugate base makes up acidic buffers. Similarly, if you talk about basic buffers, they are made up of weak base along with the conjugate acid. So weak base plus conjugate acid makes up the basic buffers, and for acidic buffers it is made up of weak acid and conjugate base. Now let's talk about buffer action. Let's finally talk about buffer action, that is the last topic, and we will be concluding our lecture thereafter. Let's take an example of acidic buffer. There is a weak acid and its salt, that is its conjugate base, CS3CO minus Na plus. Now this is the weak acid, this is the conjugate base. Now if we take an example of the dissociation, that is the dissociation of this weak acid, CH3COOH, this is slowly dissociating, and this is forming CS3COO minus, this is forming CS3COO minus plus H plus. This is how it is working. Now what happens is, when we are adding this strong electrolyte, we have to remember that this is a strong electrolyte, and obviously strong electrolytes have a high degree of ionization. Obviously it will almost ionize 100%. So what we can say here is CH3COO minus Na plus will dissociate almost completely into CS3COO minus and Na plus. Now what you can see here is there is a common ion being added. This is the common ion. CS3CO minus is the common ion. Now if you add H plus ions to this particular solution, for example, if you are adding an acid, if suddenly there is a spike in H plus ions concentration, so what will happen is these H plus ions will get combined with CS3CO minus, obviously with these CS3CO minus ions that are added extra in the form of the strong electrolyte. These two will combine and they will form CS3COH, and the reaction will move backwards. So whenever you are adding an acid, what is happening is the reaction, the equilibrium is moving backwards because of increase in this CS3CO minus CS3COH concentration. What will happen is since H plus ion concentration is increasing, it will combine with CS3CO minus and it will actually form more of CS3COH. So the reaction direction will actually shift backwards. So here there will be a overall backward shift. This is the basic concept of Le Chatelier principle, which actually says that whenever there is a change that disturbs the equilibrium, obviously it will try to nullify the change. It will actually shift in a direction that nullifies the change. So this is what happened due to this common ion effect. Also, if you take an example of addition of OH minus ions, obviously if we are adding a base, so in this case what will happen is OH minus ions concentration will increase, and here we see that there are H plus ions, water will get formed. This H plus will start decreasing. Since the H plus ion concentration will start decreasing, the reaction will actually shift in a forward direction, and it will form more of CS3CO minus and more of H plus. So this is how a buffer acts. This is how this overall concept of buffering action takes place. Whenever you add an acid or a base, there will be some action to nullify this particular change. The change will be nullified, and here the reaction will be shifting forwards. So this is the overall concept of buffer action, and this is where we'll be concluding our discussion on water, pH and buffers. I hope you enjoyed this particular session. If you like this session, do give a thumbs up, that is a like. Do comment your feedback in the comment section down below. Share this video with your friends, because this series is completely free. All the upcoming series on this channel will be completely free, and there will be quality top-notch content that we'll be delivering. So thank you so much for watching. See you in the next video. Till then, happy learning.